a different way of thinking about doing calculations. Okay? This morning, Katie introduced you to differential calculus and differentiation, which is a way of thinking about modeling the relationships between real numbers, functions, and graphs. Computers see maths in a very different way than we do. It's different from the abstract language of maths, although it shares some of the same words and concepts. And it's different from the way that we might think about solving problems. So these lectures are also a way to get you to think about how a computer actually works at the low level, because that can help you a little bit in terms of how you choose to solve problems on a computer. So what am I actually going to talk about? I'm going to introduce the concept of the loop, which is what differentiates a computer from a calculator. Okay, it's a way of doing multiple calculations, either sequentially or sometimes at the same time, and conditional statements, which allow us to choose whether or not we carry out a set of instructions. And these are the fundamental building blocks of any piece of silicon inside a computer, but also of any programming language. Then introduce another different type of loop, which is useful for solving different problems, and think about why it's actually useful to have two ways of effectively solving the same problem, why we have these different types of loops. Okay, so from a computer science perspective, what the R program is, or what you interact with, is a piece of software called a parser. Is that a word that's familiar to anyone? Okay, possibly not. It's something that's very familiar to all of you, because actually, more so than me, you can all parse several different languages, in that you can look at the words and combination of words and infer the meaning from them by their order and association. Okay? And for some languages which maybe aren't your native language, that's a process which you might have to do actively. You might have to look for certain rules, for certain combinations to make an understanding of the text. For languages that we've learned from birth, it's something that we just sort of understand. Now, a computer language in some sense is the same thing, but it's a very different type of language in that it's much more precise, but it has a syntax, it has verbs, it has nouns, okay? And the combination of those keywords allow you to perform simple or more complicated calculations. So what I mean by a parser is a piece of software that reads instructions and translates them into mathematical calculations. Okay? So when we type instructions into R in a window, we type a sequence of instructions, then R knows how to read those instructions, provided that they are written according to the rules which the language sets down. And up until very recently, this was the only way we had of interacting with computers. Now, with large language models, we almost can just talk to a computer, and it can translate what we have said into something which may or may not do the job that we want it to do. And that's because those large language models suffer from the same imprecision that we have in human language. Okay? So when R looks at an instruction like this, it reads it back to front. It goes, well, what do I want to do? I want to find this variable x. I want to apply a function to it, which in this case is the logarithm. I then want to multiply that by 5, add it to 4, and then store that value in a new variable y. Okay? So the parser understands the rules and syntax, and we need to learn the rules and syntax, so we tell R to do the right thing. So in some sense, the programming language or a script can just be a sequence of instructions, yeah? One after the other, which do the same thing each time. So that's useful for us if we want our research to be reproducible. We make a script, and then every time we run it, it does exactly the same thing. Okay? To perform a calculation that we might not want it to perform exactly the same way, each time we run it. We might want it to make decisions based on the values of variables. We may want to reuse bits of code to make the process of doing the job more effective. Okay? So the two structures that we have in computer languages to help us to do this are loops and functions. Functions are the topic of the next lecture. In this lecture, we're going to talk about loops or vector applications, similar operations, multiple pieces of data, and this idea of conditional execution. Okay. So, I am going to dissect the for loop, a structure that we have in R for doing lots of things that we want to do. Okay? So, in the middle, in these curly brackets, we essentially have a sequence of instructions. So this is just like having a list of things that we want to do. Okay? What makes it distinct or different for a loop is that those instructions can, and in most cases do, depend on what we call the loop variable. Okay, here I've called it I. Okay? And that is an index which essentially counts how many times we're going to execute this code. Okay? So in R, we have this construction, we have a keyword called for, and then we open brackets, we define the name of our loop variable. It can be anything we want. I've called it I here. And we have another keyword called in, which says we want to look at all the values, which we're going to call I, from some vector of values, which here I've called ivals. Okay? All right. Is everyone still with me? Do we understand the words I've been using? Excellent. Okay. So, ivals is this vector. For example, it could just be the numbers 1 to 10. Here I've used the colon operator, which is one of these key operators in R, which allows us to quickly make a vector of all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. All right, so let's look at an example. If we have this piece of R code, what is this going to do? Yeah.
All right, so it's going to display 1 till 10.
Yeah. I only ask easy questions. But yeah, what I'm trying to do by boring you to tears is to get you into the habit of when you look at a piece of code, stepping through in your head about what it's going to do, because that's really important to understand what something somebody else has written or something that you're writing to make sure it does the right thing. So here, it's as simple as you could get. We just loop over the numbers 1 to 10 and print them out, and that's the output that we get. Okay, super. One of the nice things about R is you can loop over a vector of any values. Some programming languages just would make you use a counting number, an integer, but we can define a vector, which is I've used the sequence function in R now to make a sequence of numbers from 1 down to 0 with an increment of minus 0.1. Okay? So if I run this loop now, yeah, instead of printing out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we print out all the values of v, which are going in reverse order from 1 down to 0. Okay? So each time we run it, we know we'll get exactly the same number of outputs, yeah, which is the length of the vector that we give it. Okay? So far, so good. Okay. Something a bit more useful. So let's say we want to calculate the factorial. So this is something which is very tedious to do by hand, and it's good to have a good thing for a computer to do because we just have to iteratively multiply together all of the numbers from 1 up to n. Okay? So this is a for loop that I've written which will do this for us. Okay? We start by defining a new variable called fact and setting the value to 1. And then we loop over the values 1 to 10, multiplying the value of factorial by I, and then assigning it back to factorial. Okay, so this is a very common trick construction that we do for using loops. We break a problem down into sequential steps. Okay, so rather than writing out all of the multiplications, we say, well, all we want to do is to keep an accumulator variable called fact and repeatedly multiply it by these values, and then we print out some output just to give the value of the factorial. Okay? It's a little bit more sophisticated. Okay? And it's a different way, this is just to illustrate, it's a different way of breaking down a problem and doing a calculation. We break it into the small chunks which we can incrementally change the value of a number, rather than just going for the actual solution in one. All right? Okay. No unhappiness. Good. Yeah?
So the fact on the fourth line, it keeps on changing each time.
Yes. Yes. So, key thing, as I've said here, the value of fact is set to 1 at the beginning, and then if you imagine there's a little arrow which is following, or is now my finger, it's following as we execute the code. We come down to here, and R says, oh, I've got a for statement. That means I'm going to want to run what's in here several times. So I'm going to do it the first time. I'm going to set I equal to 1. I'm going to take fact. I'm going to multiply it by 1, and then store, print it out, the answer, or print I pasted together with the factorial. And then when I hit the curly bracket, I'm going to look back to here, to the other curly bracket. The value of I is going to get changed to 2, okay? But the value of fact isn't changed at all. Yeah? It keeps the value that it had before.
Which in this case would be 1.
The first time we go around, yes, it's still 1. And then I is 2, so then we do 2 times 1. And then we store that, and that's 2. Okay? And then the next time we go around, fact is still 2, and I becomes 3. So we get 3 times 2, so we get 6. Amazing. My mental arithmetic never works when I'm at the lecture in front of a slide, but it worked that time. Yeah? Does that make sense?
Yes, so by after we've run this, and then when I check what fact is, it will be 10.
So I will be 10, and fact will be 3,628,800. Yeah?
So the best function is just trying to recognize the two expression in that brackets. So it's the pests.
Sorry,
Pests.
you used the word function.
Yeah, the pests there. The print statement.
The print statement.
There's a pest there.
Oh, sorry. So paste, should explain what this does. Paste just takes, you can pass it strings or numbers. In fact, I think you can pass it just about any object in R, and it will print, as in it will use the default method to make a character string. It will put a space in, and then it will put them all together. It will, what we call concatenate. Yeah? The elements. Okay, so what paste does is it just turns all of these into characters and then puts them together to make a text string. Okay, and then it prints it out. It's one of those things, it's useful if you're wanting to debug your code, to check what a loop is doing, which is why I've got it in here. Or if you're working with text data, you want to make variables which maybe have a name and multiple groups, it can be useful for that as well. So it's a useful function to know in R. Okay. Okay, so what the for loop is doing then is this is an example of conditional execution. So when we have a for statement in a script, it means we are not just going line by line through the code. Yeah, we're going to get to this point and we're going to jump back to here. It's going to do a test. Have I done all the values of I yet? If so, I jump to here. If not, I do the code again in the brackets. Okay? Does that make sense? Okay, super. Okay. Now you're happy with that, I'm going to hurt you a little bit. Because what makes loops even more powerful than just doing a lot of things at once, you can actually put one loop inside another loop, which lets us do things like if we have a big table of numbers, we can go down all the rows and all the columns, yeah? Or if we have a matrix of values, we can do something across all of those values by using two loops, where we have a variable which is counting rows and counting columns. So two loop variables now, I and j. Okay? All right. Let's just step through what this code does. Okay? So it starts by saying, so I want a for loop. I want to go through the values of I in 1 to 3. And I want to do this bit of code. But every time I go around that first outer loop, I want to run an inner loop, which takes values j from 1 to 4, okay? And it's going to now print out the value of I and the value of j, okay? So what we get is that because we're going through it logically in order, yeah? First of all, we do all the values of j for when I equals 1. Okay? So we print out I equals 1, j equals 1, j equals 2, 3, 4. Okay? And that takes us to this point, where we hit here, we jump back, R does a test and says, oh, I've still got two values of I to do, and then it loops through those, and we get 4 values of j for each value of I. Okay? Does that make sense?
Yes.
Super. So this is a way that we can, go over a matrix, or if we've got a model which has a set of populations, if we wanted to go over the whole map, we could use something like this in order to make sure that we go through all the elements in the loop. Okay. So obviously, the index variables need different names for this code to work. For those of you that maybe know a bit more about R, what would happen if I gave the variables the same name? Would I get an error? Would it work? Or what would it do? Okay, so hands up. I'm getting mumbles of all sorts.
Could you please repeat the question?
Okay, so if I wrote for I, if I used I for both of these loop variables, would that code run in R, or would it cause a problem?
It will cause a problem.
What problem?
Because we already have I there and the
Yeah.
values are 1 to 3.
Yep.
So when it comes to the second round, where it's also picking numbers from 1 to 4.
Yeah.
The I is still I. We use the same letter, so
Yes.
it would be 1 to 1. So it's like you're asking it, what are the values of 1? So what are the values of I when it's 1 to J or to I when it's
Yeah.
1? It doesn't make sense.
So logically it doesn't make sense, but will R run it?
It will run,
Yes.
but it will pick the second option because
Exactly. R will be very happy to run this for you. Yeah? And what it will do is when it goes through this loop, it will change the value of I. So you'll go through, for the first value of I, you'll do 1, and then this will change. It will change the value of I. When you end this loop, I will be 4, and it will loop round, and I'm not actually sure if it will reset the value of R. I think it will reset the value of I. So actually, it might work. It might work. Now I'm thinking about it. It might work. Logically, it shouldn't work. If you wrote this in another programming language, it would cause a huge problem because it's ambiguous. I think in R, you might get away with it because R was written by statisticians rather than computer scientists, and it has some features of the language which aren't as strict as it should be. But that's maybe one for the session, actually. I'm going to try this in the practical session. Logically, it doesn't make sense, but R doesn't check your logic. Okay? There's two types of bugs you can get writing code, and you will all hit both of these in this week. First is you make a mistake in your typing. Okay, that's a syntax error. Those are brilliant because typically R will say, oh, you can't do that, don't understand what you mean. And then you fix it and you move on with your life. A logic error is something which seems okay, R runs it, but it doesn't do what you thought it was going to do. Yeah?
Maybe a basic question, but can you run a loop without setting the vectors first, without setting what I is and what j is? Like,
Yes, yes you can. That's what the while loop does.
What I was going to ask was, well, when you're setting the vector for I and you assign it to 1 to 3, and then you wanted to do another vector of I 1 to 4, like you just replace the first I.
Yeah.
Yeah. But if you can write without setting vectors, then I guess
Yeah. I don't think when you use the for construct, it's not assigning 1 to 3 to I. Yeah, but it's labeling I into the elements of 1 to 3 each time it goes round the loop. It's a subtle distinction there. And we're going to get into a lot of fun with what's called the scope of variables. So where a letter has a unique value that's saved by R. Okay, it can cause problems with loops. It causes horrendous problems with functions if you're not careful. Okay. The inner loop can depend on the outer loop, and actually you might want that sometimes. So if you were wanting to just look at, say, the upper triangle of a table or the lower triangle, you might want to write a loop like this, where you loop over the values of I in 1 to 3, but the values of j in 1 to I. Okay? So the inner loop is part of the outer loop, which means I can just be used as a variable, and the value of I should be unchanged over this unless you change it explicitly. So the output we'd get here would be we get I equals 1, j equals 1, I equals 2. We get 2 prints for I equals 2 and then 3 for I equals 3. Okay? So we get the same numbers of outputs as the value of the loop variable for this loop. Okay? Okay. So the endpoint of the loop is different each time we go through the loop. So that's kind of useful. That's a useful thing to do. But you need to be a bit more careful thinking about how the logic of the loop. Okay. So the for loop is using a conditional check, effectively, in how R translates this thing we write as a for loop into computer code. But conditional statements are a useful thing for us to use in our code. And the most important is the if keyword, and that basically will only execute a piece of code. Again, we keep it nice and tidy and tucked away inside some curly brackets. It will only execute that code if the logical condition within the brackets is true. Okay? So a logical condition is just a comparison between a number, in this case the loop variable I, and some other number. Okay? And that could be less than, could be equal to, less than or equal to, not equal. Okay? Whole range of logical comparisons we could make. Yeah? So in this case, we loop over 1 to 10, but we're only printing out the values of I that are less than 4. So we just get 3 lines of output for this loop. Okay? All right. Should be obvious that sometimes we want a condition where if something is true, we do this. Otherwise, we do something else. Okay? That's what the else keyword allows us to do. Okay? And I know this is a bit dry and it's a bit abstract, but it will hopefully become more concrete and understandable why I'm labouring this so much once we get into the practical and try to solve some problems ourselves. Okay? So in this case, we change what the print statement is depending on whether I is less than 4 or not less than 4. Okay? All right. This is really annoying. The else needs to live on the same line as this closing brace as the if. Okay? I don't know any other programming language that does that. R needs you to do that. The R parser needs to, if the else appears anywhere other than immediately after a curly brace, a closing curly brace, you'll get a syntax error from R.
So if you drop the else,
Yep.
would you get a syntax error?
Yeah. If you put a line return there, you'll get a syntax error. Because it will say, I've got an else without an if.
No.
Yeah.
The else still with the open?
The parser for R doesn't put them together. I don't know why. It seems mad. I'm sure there's a reason for it, but that's just the way that R works. Yeah.
What for the section where the print paste is coming in? Where you wrote is less than 4. What if the symbol was used in place of it written in words as is less than 4?
If you did the less than, that's
Yeah.
fine because it's in the single quote brackets, which means it's treated as a string. So when the parser sees, so again it's going backwards, it sees closing, sees that funny dash mark and it says, oh, this is a string. I'm going to ignore everything between these 2 marks and just treat that as a variable, as a bit of text. So it doesn't interpret that. So you can put anything in there that you want. He says, thinking quickly. No, I think that's okay. Yeah. Okay. You can combine together an else and an if. Okay, so slightly more complicated. You might have a situation where you want to do something if I is less than 4, else if I is less than 7. We do something else. Else is the sort of final failsafe. Yeah, so this code executes, so we get these 3 different statements being printed. Okay. This is an incredibly boring example, but if you have a problem where you want to do something, if a set of conditions are true or not, you can write code to do that using if and else constructions. Okay. There is no, for any particular job that you might want to do, or way that you might want to sort or categorize different variables, there's no single solution to it. You could actually write this in lots of different ways using different logical comparisons, which are completely equivalent. Okay? There will be implications. Some ways of writing something will be faster than others. So the less comparisons you do, the more fast your code will be. 9 times out of 10 that doesn't matter unless you're working on a very complex individual-based model which takes days to run. Then you really need to start thinking about how the most efficient way of doing checks like this is, because these checks, conditional checks, are very slow in terms of executing code because they interrupt the code, it makes it jump to a different part in memory, and that's much slower than just repeatedly doing the same operation. Right, that's a digression. So this is just a summary for reference of the basic logical comparisons. greater than or equal to, not equal to, using the exclamation mark. This one is important to remember because equals has the role of assignment, so of taking a value and putting it to a variable. The logical comparison is the double equal sign. So if you use a single equal sign, you will copy the value of a variable to another variable instead of comparing them. Okay, and that may or may not cause an error. Less than or equal to, less than. Okay. We could do a whole lecture just on combining logical operations. We could give you a week's worth of exercises to make sure you really understand it. Unless you've got a problem that you need to solve, you probably don't want to do that. But suffice it to say, you can, what we are doing when we combine different logical operations is essentially we are uniquely identifying a particular set of variables. Okay, now this is a type of diagram which we'll come back, we'll talk a bit about again in the probability lectures. That's kind of useful. This is called a Venn diagram. Has everyone seen a Venn diagram before? Okay, amazing. All right. It's one of these things, you know, if you're a certain age, they taught it to you in primary school. If you're another age, you've never seen one. It just depends on the schooling system, but super. So A and B then is the intersection of the elements that are in A and B. A or B is the superposition of all the elements. The complement, so of A, oh, sorry, yep. So I'm using the R, so this is OR, in R, A or B. The exclamation mark says all the elements that are not in A or B, so that's everything that's outside, okay? I had a moment there, not because I was tired and I need to sit down, but because this means something different in mathematical notation. This is the conditional probability. Okay, which is how we'll use it later in the course, in fact. But for R, this means OR. And so final test for the students, what area will be not A and B? Yeah?
Yes.
Yeah? Yeah? So it's not in A and it's in B. So not in A is everything other than in the A. So we just get this shaded circle. Okay? So Venn diagram's really useful way of sorting things out when you have got 2 or 3 different categories. Once you get above that, it becomes almost less useful. But you could still do it. But essentially, this is another type of algebra, working with logical expressions, and there's rules of algebra which you can use and in order to work out what you need a condition to be. Yeah, we don't have time to get into that.
Excuse me?
Yes.
Just go back to the slide.
Yep.
So what logic do you have if you wanted to paint also the outside to do something?
If you want to,
Exclusively plus outside
for the third Venn diagram.
this one?
So there's that black, the area painted black.
Yeah.
So if you go to the fourth Venn diagram, what would be the logic if you wanted to have B, that part of B that is painted black plus the outside?
That would just be not A. Yeah? So
Okay.
not A gives us everything apart from A. And we only focus down on this crescent because we add the extra condition that has to be not A and in B.
Okay, thank you.
Okay. This is what syntactically this would look like in R. Okay? So for an if statement, rather than just having one condition, we can combine them together by using these logical operators, and, or, and the other ones, which are a bit less common. Okay? So in this case, if I is less than 4 or I is greater than 4, then we print this statement. Otherwise, we print the other one. So only for this is only true for the condition that I is equal to 4. Okay? All right. You can never have too many brackets, because brackets ensure that R will read this in exactly the way you intend. Yeah? If I had not put, I didn't need to put an extra pair of brackets around this and this, because I knew that the way R reads this, it does this first, it then does this, and then it compares it to this. So it uses, I think it's reverse Polish logic, I think. One of those. It has rules for the order it does these operations. So you don't need to write brackets as long as you really understand those rules. But having brackets just makes it completely unambiguous. Okay. So that's for loops. For loops are great when you know exactly how many operations you want to do. So you have a vector of data, a matrix of data, you want to do something with it. You know exactly how long the loop is going to take to run. You know that it will stop when you effectively run out of data. Okay? While loop is different in that it allows us to write loops which stop depending on the value of the calculation that we're doing. Okay? That should hopefully be sparking a thought, oh, if we want to run a model simulating an epidemic, a while loop could be a kind of useful thing because we want to stop it when the epidemic's over or when it peaks, you know, that sort of thing. So it's a useful kind of construction to use in modeling. The loop variable now doesn't get initialized. Okay? A while statement just says, while this condition is true, and in fact the condition doesn't even need to have a loop in it, a loop variable. It could have no variable, just a logical expression. The while loop would still work. While this, whatever is in here, is true, keep repeatedly running this code. Okay? So if you were really perverse and you wrote while true, okay, the while loop would just keep going forever and would never stop until you interrupted it. Okay? So we can write a for loop using a while loop. Again, it's a kind of abstract thing you'd only ever do in a lecture about loops. But you can do that by defining a loop variable, giving it a value 1, and saying while I is less than or equal to 10, increment the value of I. So take I and update it to I plus 1, go round. Okay? So the first time we go round, I is 2, it's less than 10, we do it again. I is 3, 4, 5, 6, 7, 8, 9, 10. Okay? So the main body of the loop, the same again, is the calculation we want to perform. We can have an index variable, but we don't need to have one. We have a logical condition. Okay. So we've got a bit more work we have to do if we want to set up a while loop. We have to remember to initialize that index variable. We need to make sure that it's changing within the loop. Otherwise, the loop will either never start or will never stop. And we have to be very careful that the way we've written it, the while loop will actually come to an end. Okay. So we could rewrite the factorial example as a while loop, and it looks very similar. So we're just defining factorial and I outside of the loop, and then we update not just the value of factorial, but the value of I within the loop, and we get the same output as we got before. Okay? This is a more inefficient way of doing the same calculation. Yeah?
Is while a conditional statement as if, while? Is it playing the same role as?
Yes, this is a conditional check. That's exactly right. So it's saying, if this is true, execute this code. If it's false, jump, and then continue going through the script. It's exactly what it is.
Sorry?
Yeah.
You say it's inefficient because we have more words.
We've had to type more with our fingers, which, when you've got a broken arm, actually that matters to you. In terms of the computational efficiency, it's probably about the same, because the for loop will be doing similar things in the background anyway. Yeah. So actually, in terms of the machine code, this is probably just as efficient as the for loop. Yeah. The inefficiency in this case just comes from the fact that you've had to write more. Okay. That does matter, because the longer your code is, the more difficult it is to understand and to maintain. So actually having the shortest code possible to do a job is a good thing. And not explicitly having variables which aren't related to the problem you're trying to solve is also a bit dangerous. Because if you reuse the names of variables, you can make mistakes in a way that if you were using a for loop with a variable that only existed within that loop and then gets destroyed, that would be less liable to cause problems with your code. Okay? Yeah. I will often, when I say efficiency, sometimes it's human efficiency, sometimes it's computer efficiency, and sometimes it's both. Okay. So the loop counter can be updated anywhere. Okay, so the for loop would actually reinitialize the value of I. In that example where I said, what if we called them both I? It would reinitialize the outer loop to just do 1, 2, 3. That wouldn't happen in a while loop though, because we can basically change the loop variable in any way that we want within the while loop. Okay. If we change the order in which we update the value of I and the update of factorial, that actually changes when the loop terminates. Okay, so an exercise for the student, if you swap these two instructions, you would get a different set of output. Okay, and that's because the point where the loop terminates will be different. The check in a while loop always happens at the beginning of the block of code. Okay, I don't think there is this construction in R, but you can get things called do while loops, which are like a while loop, but they do the condition, the check at the end. Okay, just some problems it's marginally easier to write in that way. Okay. So, yeah, so this is the example where we go back to the original condition and we get an output here for 11, which we didn't want, yeah, but it happens because of the order in which we update the loop variable. So we print one too many in this case. Okay, and while loops will not necessarily stop. Yeah, so in this case, if we write the condition to be while I is greater than 0, and we do the same block of code, there is no way that I will ever be less than 0. Or is there?
Oh, because you keep adding 1 to
Yeah.
the I.
Would this ever end?
No.
It might actually. It might, if you, but it will take a very long time. Yes, definitely, that's true. Yeah, yeah. When your battery runs out. But actually, the way numbers are represented in computers, if you get an overflow error, it might flip back to a negative number, depending on the type of variable I is, and then it might fail. Yeah. So once you run out of space in your counting number system, it will fail, but not before then. So you have to be very careful using while loops.
I think you should write somewhere, never try this on your personal computer.
Never try it on my computer. You're welcome to do it on your computer. Okay, so while loops, a bit more work. We need to remember more housekeeping. Need to ensure the loop finishes. So why would you bother? It's an obvious. Do you know in advance for your question how often you want to loop? So if you imagine you want to find we talked about optimizing to find a maximum or a minimum. That's a perfect example of where you're not going to know how long it takes your algorithm loop based on how close you are to a value might be more useful. So there is an example in the practical, and it's based on this mathematical series called the harmonic series. The order of the things is wrong. It's a well-beloved example by our good friend and colleague Nick Cunniff back in Cambridge, who was traumatized as a child by wanting to collect a full sticker book for the Mexico 86 sticker collection. And I don't know if you have sticker collections like this in your countries, but in the UK they were very popular. You would buy a blind pack of 8 stickers, and then you had to keep buying blind packs with random stickers in them until you filled in your book. I hit the same pain recently with my 8-year-old who wanted a non-age appropriate capsule toy of Deadpool, where again you get a random toy every time you buy. Okay? The harmonic series is a way of calculating effectively how many stickers and how many capsule toys you have to buy, should the manufacturers be fair in the proportions of the different toys or stickers that you have in the collection. It also is useful in terms of describing musical harmonics and apparently stacks of books. Do you know the stacks of books example? Stacks of books. He loves the harmonic series. I think these are the 3 examples they're useful for, but I could be wrong. Anyway, if we want to calculate the harmonic series, because it's defined by an iteration, it's a natural calculation to use a computer to help us out. Okay, so let's say we wanted to calculate the 427th harmonic number, or we wanted to ask a more sophisticated question like, what is the smallest n such that the harmonic numbers are greater than 10? So the first harmonic number greater than 10. So in R, we could try and write this as a for loop by setting the value of h to 0 and then looping from 1 to 427 using the expression for the harmonic numbers. Okay, so this is the sigma notation that Katie introduced this morning. We want to sum from k equals 1 to 427 of 1 over k. So we accumulate in what we call the accumulator variable h, the value of h plus the previous value of h plus the new value of 1 over k. And you let that run, and you find that h427 is a number. I'm not as excited by this example as Nick is. I'm sorry. I can't bring it. I can't bring it. I do like that Nick's pointed out you could just use the sum function in R and actually do this much more effectively. And that's important to know. There's more effective ways of working with vectors and matrices in R. It's not the purpose of teaching you about loops. Loops will help you write more bespoke models, which can be used to, in conjunction with other packages in R to solve differential equation and stochastic models. So the first problem is a natural solution is a for loop. The second question, if we want to know when, for what value of n, do the harmonic numbers first exceed 10, this is a much more natural problem to solve with a while loop, because it's the stopping value of n that we want to know. So we write a very similar value of code. We initialize h and k. Our condition is now essentially set by the question, while h is less than 10. Update the value of k, calculate the new value of the harmonic number, and then print the output. Okay? And from that, we get that takes 12,367 steps to get a harmonic number greater than 10. I think you'll probably agree it's better getting R to do it than writing it out yourself on paper. Okay. These are very simple examples. You can construct more and more complex logic using these basic building blocks. This final slide is just a summary. Major things we've talked about: logical expressions, the structure of a for and a while loop, and conditional execution. In the practical session, we're going to task you with doing some simple jobs just to check that you've understood these concepts and can start to do useful things in R using them. Okay. Are we happy? Any questions? It's done. Oh,
Can you have a while loop in a for loop?
yeah. Or vice versa.
Oh,
Yeah. At some point, you're going to blow your stack, I think. Because the stack is a bit of memory in the CPU, which basically counts levels of iteration within functions. So there will be a hard-coded limit in R, how many times you can nest a loop or nest a function. So there are very elegant mathematical algorithms that you can use writing things recursively, where you just call functions of functions of functions. They can be very beautiful to write down and impossible to run on a computer, because at some point you just run out of memory. So there's some physical limits to that, but in principle, yeah, you can go wild. Okay. Shall we move on to functions? Yeah?
When you say A and B, is that different from A intersection B like this?
So
with this, what's the difference?
So A and B is the ampersand.
A and B, yeah.
Yeah, and A or B. So what we would write as the U
Yeah.
is a straight line. Is the pipe symbol.
Oh.
Okay, so this is logical OR. Yeah, so if we were going to write this in mathematical language, this would be a U, and the logical AND would be a upside down
Yes.
U. Yeah.
So the same with
It's the same, they're the same concepts. This is just how it got translated into computer science in the 70s, when everyone was using a terminal, which only had these symbols. Yeah, so a lot of this is just legacy from bad decisions back in the 60s and 70s. Okay? All right. This is a bit tough, back-to-back, loops and then functions, but then we'll get down to the fun stuff. No, that's right. Okay. Okay. Functions are the most important thing, actually, we need to teach you about programming, because functions are what unlocks the potential of a lot of the packages in R. So there's a lot of useful software written up, algorithms, methods, ways of formulating and solving models in R, which you can access as long as you can write a function in the right format which defines what your problem is or what your model is. Okay? So if you can do that in the format that the package expects, it can then do all the fancy other stuff that it wants to do, whether that's solving a set of differential equations, simulating a stochastic model, and finding an optimum, finding a maximum, using Bayesian MCMC to estimate the best parameters. If you want to do any of that with your own model, you need to be able to write a function, and you need to be able to do it in such a way that you are sure that you get the right answer and you don't drive yourself mad. Okay? And in this lecture, I'm going to step you through not just how we write a function, but how R thinks about and executes functions, because that'll hopefully help to stave off some of the really common mistakes that you get when programming in R, some of which is just our inability to keep track of what R is doing, some of which is some poor design decisions in R. But fundamentally, a function is a specially written piece of R code which maps some form of output from some sort of input. Okay? It's exactly the same word as we use for a mathematical function. It seems like it's the same thing, but it's not quite. So a mathematical function explicitly maps one set of numbers to another in a one-to-one or occasionally a one-to-many relationship. An R, a computer function or a computer code function, it returns output, it returns input, but it doesn't need to have either in order to work and to do something useful. Okay? So it's quite different. It also can take any form of different input arguments, different data types, and produce the same or completely different outputs. Or it might just put a dot on a screen, it might just make a figure. Okay? So it's a more general idea of a function. Essentially, though, again, it's just a little bit of code that's written in a special way so that R can treat it in a special way. Okay? So looking at the anatomy of a function definition, we give it a name, which can be anything we like. There's obviously some very poor choices of function names, like for, ls, while. All of the keywords in R, best avoided. We then have the assignment operator, and then the keyword function, which tells R, okay, the next piece of text that I see, I'm going to make this into a special object in R called a function. And that function is going to expect two arguments, which I'm going to call A and B. Okay? I say I as if I'm the R program. I, the R program, and we're going to call them A and B. The user can call them whatever they like. Okay? But within the function, they're going to be referred to as A and B. So within the brackets, following the function call, the main body generates output based on the value, these variables A and B, which are assumed to have been passed by the user to the function when the user uses the function. Okay? All right. So when the user uses this new function, my function, it will take the first argument, it will take the value of the first argument and call it A, and it will take the value of the second argument and it will call it B. Okay, so it's making two new variables which only exist within the body of this function. Okay, and it can then be used for a calculation here. Just square the value of A, subtract B. And then all functions need to have a return statement in any sane programming language, which says explicitly, this is the output that I want to pass back when the function is used. Okay? R is a little bit special in that if you don't have a return statement, it will just return the last line of your code, which is kind of convenient. You need to type less, but it can be a bit ambiguous. because if the last line of your code has not got a value, then you will pass nothing back. Yeah? So it's better to have an explicit return statement so that somebody looking at your code, and that somebody might actually just be future you, remember, because future you is not going to remember why you chose to write a piece of code a certain way. Yeah? Future you can see exactly what is supposed to be returned by the function. Okay. So once we have sourced, so either copied and pasted the function definition into R, sourced it in from a script file, it's then available to use just like any other function that you might use in R. So here you can use call my function with the values 4 and 2, and then assign the value of that to x, which will have a value of 14. Okay? So at the most basic level, this is a way of just saving typing, increasing human efficiency. If there's a type of operation that we do a lot, like calculating a sine function, a cos function, an exponential function, we write some code to do it once for arbitrary arguments, and then every time we want to do it, we just need to write the name of the function. So it makes our code easier to understand. It makes everything more efficient. Okay.
Excuse me.
Yes.
So, I can shout, right? When you're writing the first that function that's over there, so you write my function, you assign it to function A, comma B, close, which will close bracket, and then the curved brackets. Do you just put them right after after the end of the parenthesis?
You can put the curly bracket here.
And it will know that it's part of the first.
You can put it here. Doesn't matter.
No. What I mean is that will it know that it's part of the first line? It's together, that they're together.
Yes. So in this case, the line return doesn't matter. And again, that's what I don't understand what's going on with the if and the else statements. When R reads this, it says this. It stores this as a bit of text in memory, which is the list of instructions. And then it sees this, and it associates this with this, and it makes this into a function object, which is some extra bits of code. Yeah. So this gets glued to this. Whenever R sees a function, it expects a pair of curly brackets. If it doesn't see it, you'll get a syntax error, I think.
Okay.
I say things like this, and then I think, does R actually check for that?
No, because I just ran that line without adding any curly brackets, and it worked fine. Like it assigned my
You've
function.
got an empty function with which does nothing.
Yeah. I just wrote
and
my
again,
function.
that's insanity. It's insanity. And that only makes sense because you don't need a return statement. So you don't actually need any code for a function in R. Okay. Computer scientists are crying somewhere in the corner about design choices. Okay. Happy? Okay. Okay. I'm going to do this exercise, which I encourage you to do this as you go through the practical as well. You're going to be sitting in front of R, so you can just type things in and see what the answer is. But actually, when you write a function, it's really important to think through what the output is going to be for different arguments before you even try and run it. Okay? And it's a great exercise to understand how pieces of code work. So for a nice simple example here, we pass 4 and 2. We saw we get the value of 14. If we reverse the arguments and put 2 and 4, okay? So it's the same values going in, but R uses the order to assign the values to A and B. So in this case, we get 0. If we just pass one argument, R gets upset. So we get an explicit syntax error that B is missing. okay? Because it tried to use B and it couldn't find it. Didn't have a value of B to do the calculation, okay? Think it's a poor design decision that the error happens here and not here, yeah? Because if you're, for some reason your code didn't depend on B, it would just work. But that wouldn't make sense because you had said that it needs that argument, yeah? So again, that would be a dangerous piece of code. Okay. This is a kind of useful R feature. If we explicitly say B equals 4, A equals 2, R will ignore the order. Okay, so if you name variables, it will use the name first rather than the order. Okay? That's fairly logical. I think that makes sense, yeah? So we've written, so the order here, we've got 4 and 2. We don't get the value 14 because we've said, no, I don't want to set 4 to A. I want to set 4 to B and 2 to A. Okay? Yep, okay. So order is important, but we can override this by using named arguments. Another useful feature is we can set a default value. Okay, so actually we could have avoided that error if we set a default value for B. Okay, so if the user doesn't give an argument, then we'll just assume a value and we get a value, we do the calculation using the default value where we don't specify B. But if we specify B but don't specify A, again we get the same error as before. Okay. Another quite nice feature of R is we can use this ellipses operator to say, the user might want to pass in other arguments, okay? And R will then allow you to pass those through to another function, okay, by just specifying the ... So that could be any number of arguments, okay? So this is something that's used a lot in sort of base R functions. In this case, you could imagine you want to do, so here I'm taking the values of x, doing a sequence from A to B with 1,000 elements, and then I'm going to plot x and sine x, but I'm going to also pass these extra arguments through, so we can use the plot sine function with just 2 arguments, and we get a sine function. If we pass through some extra graphical arguments, and we could pass as many as we want, we can change the elements of the graph. Okay. All right. These are just nice features of R which can be useful. As I said already, the return is not necessary. We can also return multiple values. So different ways of doing this. We could define a vector. So we could have a function here which concatenates the values of A and B, but in reverse order. And this my swap function takes 2 and 4, and it returns a vector with 4 and 2. Okay. Return values are all the same type. The easiest thing is to just concatenate them into a single vector. If they are different types, and I mean you might have a number, a matrix, a bit of text, a model output from a statistical package, then you can combine them together in a list, which is another general purpose container or data object in R, which can hold any different type of object. Okay, and it's a slightly different syntax. Hopefully you've all seen, at least briefly, using these double arrow brackets rather than the single brackets. Okay. This is the part of the lecture where I try to give you some superpowers. the superpower to avoid writing code that you don't understand what it's doing. Okay? There's a concept in computer science and in programming languages called scope, about where variables can be accessed by functions and by parts of the program and the software and the operating system, and where they are protected and can't be accessed. R is a bit loosey-goosey with how it does this. Okay? So we're just going to step through and think about what happens when we define a function, okay, and how R defines and uses functions. So when we define a function, what it does is it grabs a bit of memory and it puts into that memory the instructions which are within our function. Okay? The things that we want done when we say we want to use that function. Okay? It adds an entry into what's called the workspace, which links this location in memory with a name, a useful human-friendly name like my function, which will show up in the global workspace on your right-hand pane in the default view of RStudio. Okay, you'll be able to see there's a function there. If you click on it, you'll be able to see what the code is. Okay? When we call a function, so when we use a function, we say, oh, I want to do my function with the argument 3, then R goes through another series of events. It makes some new objects. Okay? The first thing it does is it creates a new and separate memory space which is just local to the function. Okay? So there's the global memory space where you have all your data that you're working on, you have your function definitions. When you run a function, it makes its own special, secret local memory. Okay? And in that local memory, it places the value of all of the arguments that you pass to the function. Okay? So there's a copy made. Takes the value, copies it to another argument. Okay? The code within the function will then execute only seeing the arguments within the function, and it will generate the output, which can then be returned to the main program, okay, to the command line, or to a variable if you assign it to a variable in the global workspace. And then it destroys that local memory space, and you never need to think about it again. Okay, so everything that happens in the function disappears, don't need to worry about it. All we get back is the output which the function defines. Okay? So, we can see this visually if we write a for loop. Using the ls function, which tells you exactly what objects are existing within a particular environment. Okay? So if we write a function like this, which makes 2 temporary variables and then returns the sum of those variables, okay, then those variables temp1 and temp2 will not be visible outside of the function. Okay? Even after you've called the function, you won't ever be able to see temp1 and temp2. The user shouldn't need to know what goes on inside the function. Okay? So if we run ls after we've typed this into the workspace, we see that there's the global variable 42 and there's the function. Okay? And after we print the value of the function, 54, we run ls again, we've got exactly the same objects in our workspace. Okay? Nothing's been created, nothing's been destroyed. Okay. So, what happens if we use the ls function within our function to print out what variables exist? Okay? So, the first version outside of the function gives the global variable and my function. If we print value of my function, it now prints out temp1 and temp2 because they exist in the local workspace. And then we come back to the global workspace and they've disappeared and we only have global var in my func. Okay? Happy? Not happy. Okay. So, if we source this code into R, what does it do? Well, it makes an object called myfunc. Okay? So you'll see that in the global workspace in the pane on the right-hand side. And do feel free to just do this if you've got RStudio in front of you. Yeah? You can just do it now. We also create a global variable which we give the value 42. And when we run the ls function, it tells us there's only two objects in the workspace called global var and myfunc. Okay? All right. Now inside the function we have put, we have asked it to return not the value of temp1 and temp2, but the value of ls. So ls prints out the contents of the memory of the function. Okay? So this time, when we print the value of the function, we get temp1 and temp2. We do not get global var. Okay? Global var isn't there because it's not inside the function. We just see temp1 and temp2. So temp1 and temp2 live inside the function. That is their scope. They are local to the function. They don't exist in the global workspace, which has this other variable, which has the value of 42. Okay? Then once the function is finished running, we do ls again. We still, temp1 and temp2 have disappeared, and we just see the global variable, which is still there, and the function definition, which is still there. Okay? Okay. So, changing the value of an argument inside the function doesn't change its value outside of the function. Okay, that should be obvious from the last slide, yeah? Because even if it has the same name, it's not going to change in the global workspace. Okay, so this bit of code takes an argument, it squares the argument and returns the square value. Okay, so if we start with that, my number is 2. We pass the value of my num to the function square value. It is not passing this number or this object, my num. It's passing the value of my num. Squares it, it returns it, which gives the value of 2. So the value of my num is completely unchanged, whereas the new variable my num squared is the square. Okay? This is one of those things that's maybe so obvious, you're wondering why I'm laboring it so much. Okay? But there's a good reason why I'm laboring it. Okay? It doesn't have to work like this. If we passed this object into the function and then changed it, you know, that could be a way that we wrote our programming language. That's not how R works, though. Okay? Yeah? In order to, you will only change the value of my num if you explicitly ask a different value to be assigned to it. A function shouldn't do that without the user asking it to change. Okay?
Sorry.
Yep.
So, when I read, this was not what I was expecting. I was expecting rather like having, for instance, 2 square outside of the function, like in the global space,
Mm-hmm.
and then have it as well inside the function.
But it doesn't exist outside. So we'll come to that. We'll come to that. So if there was a variable called toSquare in the global workspace, some odd things can happen in R. Okay. The first thing to be important to get straight in your head, though, is that by default, when we pass an argument to a function, it's only the value of the number that is copied rather than the object itself. Okay? Okay. This is where it gets complicated. R will allow functions to read in the values of variables that are in the global workspace, even if you don't pass them as arguments to the function. Okay? This is insanity. Yeah? The whole point of writing a function is so that what goes on in here isn't impacted by anything other than the arguments that you set it. Yeah? R, though, very happy. You define a global variable of 42. Yeah? So you've got the global variable in the function. You run the function, okay? And inside the function, it creates, first of all, the code just works, even though you had no argument called global var. It creates a value, a variable called global var, which is not the same one. Yeah, it's a new one. So it copies in the value of global var from the global workspace, divides it by 2, makes a new argument called global var. Okay? So we get these 3 arguments now inside the 3 objects inside the function. Function finishes, we've still got our original 2 objects, and the value of global var is unchanged. Okay? Yeah? So this code only works because R pulls in the value from the global workspace. It allows you to change it, but then it throws that value away. And the original workspace value is completely unchanged. Okay? Okay.
This means it's first check into the function if that object exists. If the object does not exist, then you have to take it.
It looks to the global workspace. If it's there, it uses it, doesn't say anything.
Change it from the.
If it doesn't find it, it will throw an argument. It will throw an error. Okay. It's sort of indirect action you don't really want in a programming language because you can't anticipate what the output depends on something which is just inside the workspace. There's a good reason why R lets you do this, and that is if you were working with, instead of just a number, let's say you were working with a genome sequence, which is several gigabytes of data, you wouldn't want to copy that into the function because you'd run out of memory on your laptop. That's another thing to run on someone else's computer, not your own. Yeah. So it makes sense if you want to work with large data sets to be allowed to do this, but you need to be aware that R does this to avoid getting yourself into a pickle. And the pickle can come in if you forget to define a variable and R just starts pulling in values from the global workspace because you've used the same name. Okay? And that causes horrendous issues and is really difficult to debug. Okay? We've got an exercise just about that idea of scope. To make matters even worse, and this is one of those things I'm showing you for completeness and I want you to forget immediately, R also has this double assignment operator, which allows you to explicitly take a value, change a value in the global workspace within a function. I can't tell you how dangerous that is. Yeah, it's insanity. It's insanity. Because if you don't know the contents of that function, you could be overwriting, your raw data. There's just so many things can go wrong with that. Again, it solves a useful purpose for someone sometime, but 99% of the time, you never want a function to work like this. Okay, so it gives you function side effects. Best avoided. Okay, that seems like a list of abstract warnings, and I think it's useful to talk through what these objects mean and how you interpret them, why they're written like that, why the language is constructed like that. Yeah, because that is the main difference between a human language and a programming language. The programming language is written to guide you to write things which will be efficient, both from the human perspective, but also from the computer perspective. Okay? There's no substitute to just trying it yourself, and that's why we will now be launching into our first practical session after the coffee break. How am I for time? Not bad, 5 minutes late. Okay. Coffee break first, and then practical session for the rest of the day. Yeah? Okay. Fantastic. I'm finished. It's your hard work now. Yep.
So I've learned through the hard way that, see the dials I was getting?
Mm-hmm.
I've learned through the hard way that